Semiconductors, that's what we're going to talk about today. And we're going to talk about the material aspects and the properties of semiconductors. Semiconductors are very important to all electronic devices. They are the cornerstone of making all the electronic devices. So they're very important. And that's why we're devoting this whole chapter for the study of semiconductor materials. Semiconductors are an important class of materials, as I pointed out. They are used in solid-state devices. Irrespective whether they're electrical devices, as we do in electronics, or whether they're optical devices, as we do in optoelectronics, or even mechanical devices, as we do in, or magnetic devices, or biochemical devices, as we do in the case of sensors. Semiconductors could be made from one single atom and one single element repeated to form the solid. Or it can be made from several atoms bonded together to make the solid. So they are either elemental semiconductors made up of one element or compound semiconductors. So elements that are made from semiconductors that are made from a single element are called elemental semiconductors, and semiconductors that are made, examples of elemental semiconductors are group 4 elements in the periodic table, like silicon, germanium. They're both group 5 and they're both elemental semiconductors. Very important semiconductor, of course, we know is silicon, where we make all our integrated circuits. Compound semiconductors, on the other hand, are those semiconductors which have two atoms in their basic basis, that is, in their basic structure that makes up the solid. These two atoms can be atoms from group 3 and group 5, and these are called 3-5 semiconductors. Examples like gallium arsenide. Gallium is group 3, arsenic is group 5, so gallium arsenide is a compound semiconductor. Compound semiconductors also may be group 2 and group 6, like cadmium telluride. Cadmium is group 2, tellurium is group 6, so cadmium telluride is a semiconductor. Zinc oxide. Zinc is group 2, oxygen is group 6, so zinc oxide is an is a compound semiconductor. So semiconductors are either elemental or compound. Okay. The most important semiconductor, which is an elemental semiconductor, is silicon, which is the basic material that we use for our electronic devices. Gallium arsenide, however, is a compound semiconductor, and it's mainly used for optoelectronic applications. So for optical devices, we use gallium arsenide. Also, high-speed devices can use gallium arsenide semiconductor for devices, and those devices would be much faster than silicon. Let's look at some semiconductor materials. Germanium and silicon are elemental semiconductors, as we said. So these are elemental semiconductors. And those elemental semiconductors, silicon and germanium, look at the band gap for these semiconductors. 0.66 electron volts for germanium, 1.12 for silicon. All the rest of the semiconductors listed here are compound semiconductors, and as you can see, they're made up of two atoms. Like here, you see indium antimonide, you see indium arsenide, you see indium phosphide here, you see gallium arsenide. So these are all, you see gallium antimonide here. All of these are 3, 5. Okay, so these are 3, 5 compound semiconductors. Indium is group 3. Antimony, arsenic, phosphorus are all group 5. Or lead selenide or lead telluride, these two here. Lead is group 2, selenium and tellurium are group 6. So these are 2, 6 semiconductors. Okay, look at the band gap. The band gap here starts very small for these compound semiconductors, and then it grows up to 1.44 electron volts in gallium arsenide. Okay, and then again it's a small in these compound semiconductors. Okay, now I want you to note one thing, that these elements here, the elemental semiconductors, are group 4 elements, one element. Here, compound are group 3, 5. Here, compound are group 2, 6. Always the average is this 4. So that is how I remember those. So the average of 2 and 6 is 4. The average of 3 and 5 is also 4. So on an average, we have an elemental covalence of 4 for elemental and compound semiconductors. The crystal structure of many semiconductors is in cubic structure. So that is why when we go back, to chapter 3, we focused on cubic cell. So the structure is cubic, but it's not one of the cubic structures that we discussed. That's the simple cubic, or the body-centered cubic, or the face-centered cubic. It's a slight offshoot of the face-centered cubic. It's a displaced form of the face-centered cubic. It's called the diamond lattice, or the diamond unit cell. Why is it called the diamond lattice or the diamond unit cell? Because it's the same unit cell for diamond. Diamond, is the form of carbon, and it's a crystalline carbon, and it crystallizes in a cubic structure, a special cubic structure, which is called the diamond structure. The diamond in itself, or with carbon, is group 4, but it has a very wide band gap, 6 electron volts. So that makes it almost insulated, even though in principle it's group 4 and it can be considered as a semiconductor. But in reality, it's an insulator, and it's a cubic structure. But it's a complex cubic structure. It's interleaved face-centered cubic. So it's like basically a face-centered cubic, but it's as if you have 2 face-centered cubic unit cells superimposed in one another, and then you move one of the unit cells 1/4 the distance along the cube diameter. And then you cut out a cube out of this structure, and that will be the diamond structure. Compound semiconductors also have exactly the same unit cell in the structure. So it's cubic, and it's a diamond structure. But because this cubic structure for a compound semiconductor has 2 elements, then it's a diamond structure where you have 1 element, and then in the next side you have another element. So it's an even more complex diamond structure. That's why it's called the zinc blende structure. So a zinc blende structure is that diamond structure. In the diamond lattice, as we will see, there are 4 nearest neighbors to any atom. So each atom in the structure has 4 nearest neighbors to the atom. Okay? So in both elemental and compound semiconductors, there are an average of 4 valence electrons per atom because of this network. Let's look at drawings of these. Here is the diamond structure. You can see all the silicon atoms sitting in a cube, but you can see that this cube is much more complex than the simple cubic or the face-centered cubic or the body-centered cubic. We have more atoms inside this cube and at the faces. And this comes from the 2 face-centered cubic that are displaced with respect to one another and getting a cube out of it. One thing you see that this atom here has 4 nearest neighbors. So these are the nearest atoms to this one here. And these nearest atoms, no, sorry, it's I made the wrong one, this one here. Okay, so this one I don't think it's right. Okay, so these 4 cross atoms are the nearest to this marked or checked atom. And you have 4 bonds, covalent bonds, attached, to the atom to the 4 nearest neighbors. So the network is covalent bonding of atoms. So you can think of each one of these atoms as silicon, and therefore you have silicon bonded tetrahedrally to 4 neighboring silicon atoms, and therefore completes the silicon network or the silicon solid. Okay? Here you have the zinc blend, right? So what we have here is a zinc blend structure. So this is the diamond here, whereas down here we have zinc blend, which is the same thing. It's a cubic lattice, but you can see that we have zinc atom and this is zinc sulfide. So zinc and sulfur. Sulfur is group 6. So this is 2 and this is 6. Okay, so it's group 2,6 compound. You can see here you have the zinc atom and here you have the sulfur atom, and you have the bonding. Each zinc atom is bonded to 4 neighboring sulfur atoms, right? So as you can see here, this zinc is bonded to these 4 neighboring sulfur atoms to form the network. So this is called the zinc blend. Okay, now in a perfect semiconductor, that's as perfect as it could be, and at absolute 0, that is temperature T equals 0 Kelvin, and we said that in the previous view graph, in the previous chapter, that we don't have any electrons available in the conduction band, right? We don't have any free electrons. That's at 0 Kelvin. So a semiconductor is like an insulator in terms of the band diagram. At 0 Kelvin, it has completely full valence band, and it has completely empty conduction band. Therefore, it behaves like an insulator. But we said, because if you remember, we had the conduction band, bottom EC here. So we're talking about the 2 topmost bands, and we have a valence band. This is all full with electrons. This is completely empty, and we have a band gap, which is EG. Okay, and this band gap luckily, is small in semiconductor. So if we increase the temperature, then we can have electrons leaving the band, getting enough energy, the valence band, and going to the conduction band. Now, if we don't have this, then all these electrons here in the valence band, look, the name or the term valence come from covalence, come from covalent bonds, right? Similar word. All these electrons here in the valence band are occupied in the covalent bonds. So what's happening is that all these electrons are localized. They don't move away from the valence bond. So they're all in the valence bonds, and therefore they're all in the valence band. So if you put in an electric field, nothing happens. We don't get any current flowing. However, when you raise the temperature above absolute zero, some of these electrons, as I said here, would have enough energy to break loose from these covalent bonds, to leave the covalent bonds, and then make it to the conduction band. When they make it to the conduction band, they become free electrons. So how do electrons become free? Is when they're able to leave the conduction band, leave the valence band, and go to the conduction band. In chemistry terms, leave the covalent bonds and become free electron. So, in other words, if you go back here, you have electrons here in the covalent bonds, right? 2 electrons for each bond, okay? And so the electrons cannot move. They're all within these bonds, right? So if you give them enough energy, then an electron could get out of this bond and becomes a free electron. Once it becomes a free electron, that means it's an electron in the conduction band. These electrons in the bonds are not free to move. They are all within the bonds, so they're valence electrons. So that's the chemistry picture, for the physical picture that we showed from quantum mechanics. So the overall picture is we need to give energy to electrons in the valence band, in the bonds, so that they become free and they can conduct. So that's the whole picture. That's how we make a semiconductor, which is essentially an insulator at absolute zero. That's how we make it conducting. Now, here is a very important concept that actually shows up when we talk about semiconductors. And this concept is the concept of holes in a semiconductor. And to illustrate holes and the idea of holes, we are going to use an elemental semiconductor and namely use silicon. And what I will do is I will look at a two-dimensional representation, two-dimensional hypothetical silicon solid. Okay? We know that the solid is three-dimensional, but we're going to look at a hypothetical two-dimensional silicon solid. So I'm going to clean up this a little bit. And here is the silicon, okay, network. I told you that in the network you have bonds, okay? So you have a silicon atom, and then you have covalent bonds to the 4 nearest neighbors. Each silicon atom contributes an electron, and then you complete the valence bonds. These electrons at 0 Kelvin are all in the bonds. So they are all in the valence band. They are all filling the valence band, so the valence band is completely full, and there is no conduction, there is no electric current. Now, let's increase the temperature now of this silicon. We are assuming that this silicon crystal is a pure silicon crystal, nothing just but silicon. And it's a very organized, uniform network of silicon. We are assuming that it's two-dimensional, so we are not being realistic because we know silicon Solid is three-dimensional. But here we're just trying to explain the concept. So now you increase the temperature, and as the temperature is increased, okay, these electrons in the bonds become energized. They get more energy and more energy. They can get enough energy to break away from the bonds. And if they break away from the bonds, they become free electrons. They no longer belong to this bond. They are now free, belonging to the whole crystal. And again, another electron here got enough energy to become a free electron, liberated from the bond. Okay? What do they leave behind? They leave behind a need for electron, a hole of an electron, a loss of an electron, if you like. So there is an electron needed here. So you have a hole here. And because the electron has a negative charge, this hole, when the electron leave, then all of this region here becomes positive in charge, because we need an electron to make it neutral. So the positive charge here is the same as the electron charge, which is 1.6 times 10 to minus 19 coulomb, right? That is the charge we need to fill that hole. And we need a negative charge to fill that hole and make it neutral. So the charge in this region here, or in this hole, is positive 1.6 times 10 to minus 19. Now, this electron here can jump to this, because there is a positive charge, get attracted very quickly and fill up this hole. But if the electron jumps and fills up this hole, what does it leave? It leaves a hole behind here. So the positive charge moves here. And then this electron can see the attraction and jump here. And so the positive charge moves here. So just like this electron is able to move and free, this positive charge or hole is able to move, and it is actually free. With very little energy, it can move. So what we get when you have a free electron here, it leaves behind a free hole. And this is a very interesting concept. In terms of bands, we have the conduction band, okay, and we have the valence band, okay, and we have the band gap right here, Eg. And the picture at t equals 0 is such that there is no free electrons in the conduction band, and the valence band is completely full. So this is this network with all the bonds occupied. Okay, so that's what we have here. But now, if we increase the temperature, as we said, and I'm describing this in the band picture, what happens is an electron has enough energy now to go up here and becomes free electron, right? Which is an electron in the conduction band now. And what does it leave behind? It leaves behind a hole in the valence band, and this hole also is free to move. So it's free hole, okay, in the valence band. The electron has a negative electronic charge, which is 1.6 times 10 to minus 19 coulomb. The hole has a positive electronic charge, which is 1.6 times 10 to minus 19 coulomb. Now, if we put a voltage across here, right? So let's again clean this. If we put a voltage, right, and say we make this voltage plus minus along, at the two ends of this semiconductor, then electrons would move this way and generate an electron current. But also holes which are positive, so this electron move this way and the hole move this way. So holes will move this way. Okay, so here you get holes moving to the negative polarity, and you get electrons moving to the positive polarity. So you have free electrons and free holes, and they're both moving to conduct. So in a semiconductor, we have both free electrons as well as free holes. So in a semiconductor, you have free electrons and free holes. In a metal, we only have free electrons. Because you remember when we talked about the metals,